Tonight, we're going to explore one of the most overlooked structural principles in all of physics. The principle is rotation, and the quantity behind it is angular momentum. Every electron carries a spin of 1/2. Every proton, the same. Photons carry a spin of 1. The Earth turns at 1,674 kilometers per hour at its equator, faster than the speed of sound at sea level. The Sun completes a rotation roughly every 25 days. Our galaxy carries the Sun around its center once every 225 to 250 million years. A single revolution astronomers call a galactic year. Every gravitationally bound system in the universe rotates. Every particle has intrinsic spin. Angular momentum is conserved perfectly at every scale without exception. And yet, when you sum all of that rotation across the entire observable universe, the total comes out to essentially zero, an almost perfect cancellation, an unexplained one. By the end of tonight, you're going to understand why spin runs through every layer of reality from the electron to the galactic year, how angular momentum is conserved without ever telling us where it began, and why this hidden cancellation may be the only thing protecting the structure of time itself. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The room feels still. The chair beneath you is still. The floor, the walls, the air, the cup sitting on the table, all of it perfectly motionless. None of it is still. Right now, if you are standing somewhere near the equator, you are moving eastward at 1,674 kilometers per hour. You are already supersonic. You have been your entire life, and you have never felt it once. That is not a perception failure. That is not the body being fooled. It is the body working exactly as it should. Here is what is actually happening. Your nervous system does not measure motion. It measures changes in motion, acceleration, deceleration, the jolt when a car stops suddenly, the pull when a plane banks hard. Smooth, continuous, constant rotation generates none of those signals. It reads as silence. The stillness you feel in this room is an accurate description of your reference frame. You and the chair and the floor and the walls are all moving at exactly the same speed, in exactly the same direction. Relative to each other, nothing is moving at all. The stillness is real. It is just not the whole story. Earth completes one full rotation every 23 hours, 56 minutes, and 4 seconds. Not 24 hours. That extra 3 minutes and 56 seconds is the time Earth needs to catch up to the position of distant stars, a subtlety astronomers call the sidereal day. The body registers none of it, not the sidereal day, not the 23 hours and 56 minutes, not a single second of the rotation. Something else was happening. The stillness does not stop with your body. It extends outward into the entire envelope of the planet. The atmosphere co-rotates with the surface. So do the oceans. The jet streams, which flow at altitudes of roughly 10 to 12 kilometers above sea level, are also locked into this synchronized spin. Gravity and friction drag the entire fluid shell of the Earth into motion with it. So if you step outside, the air around you is also moving at close to 1,674 kilometers per hour at the equator. The ocean current you could sail across is also spinning. The cloud system forming over the Atlantic is also being carried. The whole envelope moves together. The illusion of stillness is total, and yet the rotation is always writing its name somewhere. The Coriolis effect is the visible signature. Earth's rotation deflects moving objects. In the northern hemisphere, the deflection is to the right. In the southern hemisphere, it is to the left. This is not a dramatic force at small scales. You will not notice it pouring a glass of water, but scale it up to a weather system hundreds of kilometers wide, and the effect becomes decisive. Hurricanes in the northern hemisphere spin counterclockwise. Typhoons in the southern hemisphere spin clockwise. Those spiraling arms you see in satellite images of storms are the Earth's rotation made visible. The planet cannot stop announcing itself. It only hides at the scale the body can touch. That is the scale of the surface. Now consider how far down the rotation actually goes. Drop beneath the level of weather systems, beneath the ocean floor, beneath the crust and the mantle and the iron core. Go all the way down to the atoms that make up the chair, the floor, the walls, the body. The rotation does not stop there. It changes form. Every fundamental particle carries something called quantum spin, an intrinsic angular momentum-like property built into the particle itself, not something rotating around an axis in space, not tiny balls spinning the way a top spins. The mathematics of quantum spin behaves like angular momentum and produces measurable effects identical to angular momentum, but quantum spin cannot be described as literal rotation. What it physically is remains one of the genuinely open questions in physics. For now, the important thing is this: every particle has it. Every proton, every electron, every quark inside every proton. It never turns off. Hydrogen carries this into a frequency you can actually measure. Hydrogen makes up roughly 75% of all ordinary matter in the universe. In a hydrogen atom, the electron and the proton each have their own spin. They are usually oriented in opposite directions, anti-aligned, the lower energy configuration. Occasionally, the electron flips to align with the proton. Then it flips back. When it does, it releases a photon at a precise frequency: 1,420,405,751 Hz, or about 1.42 gigahertz. That is the hydrogen hyperfine line, the most precisely known frequency in nature, used by radio astronomers all over the world to map where hydrogen gas lives in our galaxy and beyond. Point a radio telescope at any region of the sky, tuned to 1.42 gigahertz, and you are reading the spin states of hydrogen atoms flipping between energy levels across distances of thousands of light years. Every hydrogen atom in your body participates in this. The spin is not something that happens to hydrogen. It is part of what hydrogen is. Now stack the whole picture. Your body is being carried eastward at more than 1,000 miles per hour on Earth's surface. Earth is orbiting the Sun at roughly 30 kilometers per second. The Sun is moving through the Milky Way at approximately 230 kilometers per second, tracing a slow arc around the galactic center. The Milky Way itself is falling toward the Virgo cluster at roughly 600 kilometers per second. And underneath all of that, at the level of every proton and every electron, quantum spin runs continuously without any energy input at all. Think about what this means. There is no level of reality where motion stops. There is no layer you can descend to where things are finally at rest. The stillness of the room is not the baseline. It is a local agreement between objects moving together. Strip that agreement away, and the motion is everywhere. Motion is not something that happens in the universe. It is what the universe is made of. That is the first thing rotation tells us. And it is only the beginning of what it has to say. So, what keeps any of it turning? That is not a rhetorical question. There is an actual answer. A single law, precise and absolute, threading through every scale we just described. It is called conservation of angular momentum. And what it says is this: the total angular momentum of any system not acted on by an outside force never changes. Not slightly, not approximately, exactly. Think about what that means. A spinning object, isolated from outside interference, goes on spinning forever. Not slowing down, not winding down, not eventually coming to a stop. Forever. Even at the very end of the universe. Long after every star has burned out and every black hole has evaporated. Isolated matter that is rotating will still be rotating. The law does not soften with age. It does not relax at extreme scales. It holds everywhere, at every size, without exception. That is the foundation. Now, let's build up from the bottom. At the smaller scales, the particles themselves carry angular momentum. Electrons carry a spin value of 1/2, protons carry 1/2, photons carry 1, the Higgs boson carries 0. These values are measured in units of the reduced Planck constant, which is the smallest possible quantum of action in nature. And those values are not properties the particles happen to have. They are what the particles are. You cannot change the spin of an electron without it ceasing to be an electron. The spin is not a behavior. It is the identity. The previous section noted that quantum spin is not physical rotation in the ordinary sense. That is true. But here is what carries over. The angular momentum is real. It has a precise magnitude. It participates in conservation just as rigorously as any spinning top or turning planet. When particles combine into atoms, their individual spins add together according to quantum rules. The orbital angular momentum of electrons around the nucleus adds in as well. Molecules inherit spin from their constituent atoms. Each molecule ends up with a characteristic set of rotational energy levels. When a molecule tumbles in space and shifts between those levels, it emits or absorbs a photon at a very specific frequency. Astronomers detect those frequencies in microwave light and use them like fingerprints to identify the chemical composition of gas clouds hundreds of light years away. The spin of particles, translated through atoms and molecules, becomes a map of the interstellar medium. The pattern is already clear. Angular momentum passes upward. Now move to the scale of solar systems. About 4.6 billion years ago, a cloud of gas and dust began to collapse under its own gravity. The cloud had irregular motions, turbulence from the surrounding medium, pressure waves from nearby supernova explosions, small gravitational nudges from passing objects. None of these motions cancel perfectly. The cloud had a small but non-zero net angular momentum before the collapse even began. Here is where the law becomes dramatic. As the cloud collapsed inward, its rotation had to speed up. This is the same mechanism a figure skater uses when pulling their arms inward during a spin. The rotation rate increases, but the amplification in a collapsing cloud is not modest. The rate scales with the square of the radius ratio. If a cloud contracts to 1/10 of its original radius, its rotation rate does not increase by 10. It increases by a factor of 100. The numbers are real. The cloud that became our solar system contracted by many orders of magnitude. The rotational energy it started with was small and barely noticeable. What emerged was everything. The result was not a sphere. It could not have been a sphere. A collapsing cloud with angular momentum cannot fall straight in. The component of motion perpendicular to the rotation axis gets compressed. The component parallel to the rotation axis is free to fall inward. The cloud flattens. What remains is a disk, spinning in a single plane, with the young sun burning at the center. The planets accreted from that disk and inherited its angular momentum. Every planet orbiting in roughly the same plane and in the same direction carries the memory of that original pre-solar turbulence. Earth's own rotation today is a direct echo of motions that predated the sun predated the Earth, predated the entire solar system. The spin didn't begin here. It arrived here. Stellar evolution follows the same logic. Young stars, newly formed from collapsing disks of gas, can rotate once every few hours. They are compact, and their angular momentum is concentrated. The Sun today takes approximately 25 days to complete one rotation at the equator. That is dramatically slower than its youth. Over billions of years, the solar wind carried charged particles outward along magnetic field lines. Those particles left the Sun, but stayed connected to its magnetic field long enough to drag on it slightly. Repeated across billions of particles over billions of years, this magnetic braking transferred angular momentum from the Sun into the surrounding space. The spin was not destroyed, it was redistributed. Slower Sun, slightly faster distant medium. The total remained constant. Spin never disappears. It only moves. Now step back even further. The Milky Way is a barred spiral galaxy roughly 100,000 light-years in diameter. It contains somewhere between 100 and 400 billion stars. Nearly all of them orbit the galactic center in roughly the same plane and in the same direction. At the radius where our Sun orbits, one complete circuit takes approximately 225 to 250 million years. Astronomers call this the galactic year, or the cosmic year. Earth formed roughly 4.6 billion years ago. Divide 4.6 billion by 225 million, and you get approximately 20. Earth has completed about 20 full orbits of the Milky Way since it formed. 20 galactic years. Every star in the galaxy, every gas cloud, every dust grain spiraling through the arms carries angular momentum inherited from the collapse and interactions that assembled the galaxy itself. The pattern holds at every scale: particles, atoms, molecules, moons, planets, stars, galaxies. But the most dramatic demonstration of the law in action is something called an accretion disk. When matter falls toward a massive object, whether a young star, a neutron star, or a black hole, it almost never falls in a straight line. Even a tiny sideways motion, an infinitesimally small transverse velocity, carries angular momentum. And conservation of angular momentum means that sideways motion cannot simply be shed. It must go somewhere. The infalling matter cannot collapse directly to the center. It orbits. It accumulates in a rotating disk. This is an accretion disk. Material at the inner edge orbits faster. Material at the outer edge orbits slower. Magnetic instabilities develop in the disk and transfer angular momentum outward through turbulent interactions. As angular momentum flows outward, material flows inward. The disk feeds the central object. The energy released in the inflow is extraordinary. Accretion disks around black holes and neutron stars can outshine entire galaxies. The mechanism driving all of that luminosity is not nuclear fusion. It is not chemical energy. It is gravity acting on matter with nowhere to put its angular momentum except outward. All of that power comes from a conservation law. Here is where the picture becomes something more than a catalog of spinning things. Every rotating structure we have described, from the spin of an electron to the orbit of a star around the galaxy, carries angular momentum it inherited from something before it. No angular momentum was created along the way. It was only conserved, amplified by gravity, redistributed by collisions and magnetic forces, and passed forward. Every spinning structure holds memory of motions that predated it. The universe keeps a ledger. Nothing is written off. But here is where it gets strange. Add up all the angular momentum in the observable universe. Measure the spins of galaxies. Count the orbital motions. Track the rotations in every direction. The total comes out to almost exactly zero, Not a large number, not even a small number, nearly zero. The law says angular momentum is conserved. Fine. But where did the original angular momentum come from? How did the universe start with what appears to be essentially none? And if it started with almost none, why does everything spin? That question has no clean answer, and it is the question the rest of this story will circle. One rotating system makes the question concrete. Our own galaxy. The solar system is moving right now, not the slow drift of a planet around a star. Something far larger. The entire solar system. Sun and Earth and every other planet is traveling through the Milky Way at roughly 230 kilometers per second. That is not a typo. At that speed, one complete orbit of the galaxy takes somewhere between 225 and 250 million years. One trip around the center. Earth has completed about 20 of them since it formed. Think about what that means. Each galactic orbit is longer than the entire Phanerozoic eon. That is the span of time containing every animal that has ever lived. The Cambrian explosion, when complex creatures first diversified across the oceans. The rise and fall of the dinosaurs. Every mass extinction. Every mammal. Every human civilization. All of it fits inside a single galactic orbit, with room to spare. The dinosaurs were erased 66 million years ago. Since that moment, since the asteroid and the fire and the darkness, the solar system has completed only about 1/4 of one galactic orbit. The sky the dinosaurs knew was almost exactly the sky we know. Not a completely different configuration of stars. Not a new neighborhood. Nearly the same view, shifted only slightly. And Andromeda, the farthest object the naked eye can see, sits 2.5 million light years away. The light reaching us from Andromeda tonight left that galaxy 2.5 million years ago. At that moment, the solar system had barely moved. A tiny fraction of a single galactic orbit. The universe is not just vast in space. It is vast in a way that makes galactic motion almost imperceptibly slow from any human vantage point. But the solar system is moving, and that motion carries a question. Here is what scientists expected. The galaxy is not a rigid wheel. A wheel rotates as one piece. Every part of it completes one rotation in the same amount of time, the inner edge and the outer rim turning together. The Milky Way is not like that. It is hundreds of billions of stars, each following its own gravitational path, not locked to its neighbors, not physically connected to anything. They are, for practical purposes, a collection of objects, each responding independently to the combined gravity of everything else. Newtonian gravity applied to that kind of system makes a clear prediction. The stars closer to the galactic center, where most of the visible mass is concentrated, should orbit faster. The stars farther out, where the gravitational pull is weaker, should orbit slower. This is exactly how the solar system works. Mercury completes an orbit in 88 days. Neptune takes 165 years. Outer planets orbit slowly. Inner planets orbit fast. The prediction for galaxies followed the same logic. The outer stars should lag behind. The rotation curve, a graph plotting orbital speed against distance from the galactic center, should show a clear decline, slower and slower as you move outward. Here is what the observations showed. In the 1930s, the Swiss-American astronomer Fritz Zwicky was studying clusters of galaxies, groups of hundreds or thousands of galaxies bound together by gravity. He measured how fast individual galaxies inside those clusters were moving. Then he calculated how much visible mass the cluster contained, all the stars and gas he could detect, and how much gravitational pull that mass could produce. The numbers did not work. The galaxies inside the clusters were moving far too fast. The visible mass was nowhere near enough to hold them together. They should have been flying apart, but they were not. Zwicky proposed that there must be additional mass he could not see. He called it dark matter. Not many people listened. That changed in the 1960s and into the 1970s, when the American astronomer Vera Rubin began measuring something more direct. She mapped the rotation curves of individual galaxies, not clusters. Single galaxies, star by star, measuring how far stars at different distances from the galactic center were orbiting. She expected the standard picture: faster inside, slower outside, a graceful decline. What she found was flat. The outer stars were orbiting at roughly the same speed as the inner ones, sometimes faster, not slightly elevated, not a minor discrepancy, flat. At distances where the speed should have dropped dramatically, it had not dropped at all. This is not a small anomaly. Those outer stars should have flown off into intergalactic space long ago. They are moving fast enough to escape, if the only gravity acting on them comes from the visible mass of the galaxy. But they have not escaped. They have been orbiting for billions of years. Something is holding them. Something with enough mass to provide the additional gravitational pull. Something distributed, not in the disk of the galaxy, but in a large, roughly spherical halo surrounding it. Something that does not emit light, does not absorb light, does not interact electromagnetically in any way we have detected. This is dark matter, not a confirmed particle, a name for the gravitational problem, a placeholder for whatever is actually there. The candidates are numerous. WIMPs, short for weakly interacting massive particles, which would interact with ordinary matter only through gravity and the weak nuclear force. Axions, extremely light hypothetical particles originally proposed to solve a different problem in physics entirely. Sterile neutrinos, a heavier cousin of the known neutrino that does not interact even weakly. Primordial black holes, formed in the earliest moments after the Big Bang, before any stars existed. Decades of underground experiments have searched for direct evidence. Sensitive detectors buried deep in mines, shielded from cosmic rays and surface radiation, waiting to register the faint recoil of a dark matter particle striking an ordinary atomic nucleus. No confirmed signal, not one. But the reality was different. Not every physicist accepts the dark matter interpretation. In 1983, Mordechai Milgram proposed a different explanation. He called it modified Newtonian dynamics, or MOEND. The idea was this: Newton's law of gravity might not hold exactly at very low accelerations, the kind experienced by stars on the outer edges of galaxies. If gravity behaved slightly differently in that regime, the flat rotation curves could be explained without invoking any invisible mass at all. MOND works remarkably well for individual galaxies. It predicts the shape of rotation curves with impressive accuracy, but it struggles with galaxy clusters, the same clusters Zwicky studied, where the discrepancy between visible mass and observed motion is too large for a simple modification of the gravitational law to fix, and MOND has not been successfully extended into a full relativistic theory that passes all the tests of general relativity. It remains a minority position, not dismissed, not confirmed, a persistent challenge to the dark matter picture that no one has resolved. Both camps agree on one thing: the rotation curves are telling us something real. The speeds are measured. The discrepancy is measured. Whatever is producing flat rotation curves, whether invisible particles filling galactic halos or a modification of gravity at low accelerations, the universe contains structure we cannot directly see. Rotation is the diagnostic instrument. Something massive, distributed and invisible, left its fingerprint in the motion of stars. The story of why everything spins does not end with conservation of angular momentum. It includes a chapter written in matter we have never detected, or in a law of gravity that differs from what Newton wrote. We do not know which. Decades of work have not resolved it. What we do know is this. Every galaxy we have measured shows the same signature, the same flat curve, the same mismatch between visible mass and observed motion. The problem is not local. It is not an exception. It appears everywhere we look. And the flat rotation curve is only one of the ways that spinning structures have revealed what we cannot see. But that invisibility is only one of the ways rotation has been pointing us towards something deeper. The flat rotation curve tells us something is missing from our picture of mass. There is a different question sitting underneath all of it that the curves do not answer. Why does everything that collapses under gravity end up shaped the same way? Galaxies are flat. The solar system is flat. Saturn's rings are flat. Accretion disks around neutron stars and black holes are flat. The geometry keeps repeating, and it is not a coincidence. It is a consequence. Think about what happens when a cloud of gas begins to collapse. A region a few light years across, cold, diffuse, mostly hydrogen and helium with traces of heavier elements. Some perturbation starts the process. A nearby supernova sends a pressure wave through the region. Self-gravity accumulates. The cloud begins to fall inward. The naive prediction is a sphere. Gravity pulls equally in all directions. Isotropic force should produce isotropic collapse. The gas should gather into a ball. But here is where that intuition fails. No cloud of gas in a turbulent, rotating, gravitationally complex universe starts with exactly zero angular momentum. There is always some slight net rotation in the material, a tiny bias in one direction, almost imperceptible in the diffuse cloud. And here's the critical point. That tiny rotation cannot disappear. Angular momentum is conserved. As the cloud collapses, the rotation does not stay gentle. The same law that governs the figure skater pulling her arms inward governs the collapsing cloud. As the radius shrinks, the rotation rate climbs. Not gradually. The amplification scales with the square of the radius ratio. Shrink the radius by a factor of 10. The rotation rate rises by a factor of 100. Shrink it by 100, the rotation rate climbs by 10,000. What began as an almost invisible drift in the gas becomes the dominant force organizing the collapse. Now the geometry splits. Material falling along the rotation axis can continue falling. It has no angular momentum in that direction to resist. It reaches the center and builds a protostar. But material falling from the sides carries angular momentum that pushes back against direct infall. It cannot cross the barrier. Instead, it spirals. It settles into the only configuration that both conserves angular momentum and obeys gravity. A disk. The disk is not an accident of special circumstances. It is the mathematical outcome of angular momentum conservation, overriding the spherical symmetry of gravity in the perpendicular plane. Given any non-zero rotation, a disk is what must form. And the universe almost never starts with zero rotation. Producing a perfectly non-rotating cloud would require the angular momenta of every turbulent pocket of gas to cancel each other exactly. Not approximately. Exactly. Random processes do not do that. The fine-tuned cancellation that would be required essentially never happens. Rotation is the default. The sphere is the theoretical limit. The disk is what the universe actually builds. This is why the geometry repeats. Planets orbit in a plane because the solar nebula that formed them collapsed into a disk. Saturn's rings trace the plane of Saturn's own spin because the material that built the rings settled where angular momentum conservation told it to settle. Galaxies are flat for the same reason on scales billions of times larger. Accretion disks around compact objects repeat the geometry on smaller scales still. The shape is the same because the law is the same. But the mechanism of disk formation is not the mystery here. We understand it. The question the mechanism points to is different. Every disk, every flat galaxy, every aligned planetary orbit is a record of angular momentum that was already present in the material before collapse began. The collapse did not create that angular momentum. It amplified what was already there. So where did the seed come from? Where did the original slight rotation enter the gas before the collapse started? That question does not have a clean answer yet. It will come back. For now, hold the principle. Disk geometry is the universe's signature for angular momentum conservation in action, and every disk you see is proof that some earlier motion in some earlier configuration of matter has been preserved. Now, bring the picture in closer, down from the scale of galaxies and nebula, down past planets and rings, all the way down to the atom, because rotation at the quantum scale does not behave the way any of this has suggested, and the experiment that first exposed that fact was run in 1922. Otto Stern and Walter Gerlach, two German physicists, designed an experiment to measure the angular momentum of atoms directly. The setup was precise. Silver atoms were vaporized from a heated sample and directed as a narrow beam through a strongly non-uniform magnetic field. When a magnetic moment, which you can think of as a tiny bar magnet carried by the atom, passes through a field that varies across space, the field exerts a force on it. The direction and magnitude of the force depends on how the bar magnet is oriented relative to the field. Here is what classical physics predicted. Silver atoms in a gas are oriented randomly. Their magnetic moments point in every possible direction. Each atom entering the non-uniform field would be deflected by an amount determined by its particular orientation. The full range of orientations would produce a full range of deflections. The detector plate should show a continuous smear, a band of silver distributed smoothly from top to bottom. That is what the equation said. That is what everyone expected. What Stern and Gerlach found was not a band. 2 spots. Only 2. One above the center line, one below. A clean gap between them and nothing else. Not a smear. Not a continuous distribution. 2 discrete locations where silver atoms arrived. Half the atoms went one way, half went the other. No atom went anywhere in between. The implication was immediate and uncomfortable. The magnetic moment of the silver atom did not take a continuous range of values. It took one of exactly 2 values. Atomic angular momentum was not free to point in any direction. It was quantized, restricted to discrete states. The intermediate orientations did not just go undetected, they did not exist. Niels Bohr had already proposed quantized energy levels in hydrogen a decade before, but those were energy levels in an equation. The gap between Stern and Gerlach's 2 spots was a physical gap, a space on a metal plate where silver atoms should have been, and were not. That gap was a quantization made visible. Wait, 2 spots was the wrong answer even for a quantum theory. Orbital angular momentum, when quantized, produces an odd number of possible orientations, 1 or 3 or 5. The quantum rules for orbital angular momentum are strict on this point. 2 orientations require a quantum number of 1/2. An orbital angular momentum cannot produce a quantum number of 1/2. It produces integers only. 1, 2, 3, never a half. 2 spots was impossible under the theory Stern and Gerlach thought they were testing. 3 years later, in 1925, Samuel Goudsmit and George Uhlenbeck proposed the resolution. The electron, they argued, carries its own intrinsic angular momentum that has nothing to do with its orbital motion around the nucleus. They called it spin. The spin value of the electron is 1/2, measured in units of the reduced Planck constant. Spin 1/2 produces exactly 2 outcomes, up or down, nothing in between, no intermediate state. The electron does not choose a spin direction and then get deflected accordingly. Between measurements, it exists in a superposition of both states simultaneously. The measurement forces one outcome. The Stern-Gerlach result was not a measurement of orbital angular momentum. It was an accidental discovery of something new, something the theory had not predicted and could not contain. Intrinsic spin. Not the spin of an electron moving around a nucleus. Something more fundamental than that. And here is the thing that should already be pressing on the picture we have been building. The spin that made the experiment work. The spin that showed up as 2 discrete spots on a metal plate cannot be the spin of a small sphere rotating around an axis. The numbers do not allow it. The geometry does not allow it. And what it actually is turns out to be one of the strangest questions in all of physics. Let's hold that question and follow it down. The numbers do not allow classical rotation. The geometry does not allow it. So what does allow it? That is where the story goes next. And the answer is not a refinement of the classical picture. It is the complete replacement of it. The year was 1925. 2 graduate students in Leiden, Samuel Goudsmit and George Uhlenbeck, were working under Paul Ehrenfest. They were trying to explain a puzzle that had irritated physicists for years. When atoms are placed in a magnetic field, their spectral lines split. That much was expected. Orbital angular momentum accounted for some of the splitting, but not all of it. There was always extra splitting. Too much. The pattern that theory predicted did not match the pattern that spectroscopes recorded. This was called the anomalous Zeeman effect, the anomalous magnetic splitting, the result that refused to fit the standard accounting of atomic angular momentum. Goudsmit and Uhlenbeck proposed an answer. The electron, they suggested, carries its own intrinsic angular momentum, not angular momentum from orbiting the nucleus, something internal. The electron spins. Here is what the numbers required. If the electron is a small charged sphere spinning on its axis, and if that spin must generate the observed magnetic moment, the surface of that sphere would have to move faster than light. Not slightly faster. Not a few percent over the limit. Orders of magnitude faster. Special relativity forbids this. It forbids it completely and without exception. The classical spinning sphere model was ruled out by its own arithmetic the moment anyone checked. Goudsmit and Uhlenbeck realized this immediately. They tried to withdraw the paper. Ehrenfest had already submitted it. He told them they were young enough to afford a stupid idea. But the idea was not stupid. The model was wrong. The resolution is strange enough that it still resists easy description. The electron is not a small sphere. Modern physics treats the electron as a point particle. No spatial extent, no surface, no radius at all. A point cannot rotate in any geometric sense. There is nothing to rotate. No axis, no surface speed, nothing that could exceed the speed of light, because there is nothing that could move. And yet, the electron carries angular momentum of exactly 1/2, measured in units of the reduced Planck constant, every time, without exception, regardless of speed, environment, temperature, or experiment. The value never varies. It is not generated by motion. It is not produced by the electron's shape. It belongs to the electron's quantum state the way charge belongs to it, the way mass belongs to it. Change the spin and you no longer have an electron. This is what spin is, not rotation, a property as fundamental as charge, a property the particle cannot exist without. Now, follow that one step further. In 1928, Paul Dirac set out to write the relativistic quantum equation for the electron. The existing quantum equation, Schrödinger's version, worked but ignored special relativity. Dirac wanted to bring the two into alignment. He was not trying to predict anything new. He was trying to write a consistent equation. But here is where it gets strange. The math followed wherever it led, produced a wave function with 4 components. Not 2, not 1, 4. Dirac did not put them there. He did not add them for convenience. The equation demanded them. 2 of the components described spin-up electrons and spin-down electrons. That was expected. The other 2 described a particle with the same mass as an electron and opposite charge. A particle that did not yet have a name. A particle that had never been observed. Consider this. Dirac's equation predicted the existence of a new particle purely as a mathematical consequence, not as a guess, not as a hypothesis, as an output of the arithmetic. In 1932, 4 years after the equation was published, Carl Anderson was photographing cosmic ray tracks in a cloud chamber. A particle curved the wrong way in the magnetic field, the same curvature as an electron, but in the opposite direction. Same mass, opposite charge. Anderson had found the positron. He won the Nobel Prize. Dirac had predicted antimatter without looking for it. The lesson is blunt. Spin is not optional. Any point particle described by a relativistic quantum theory must carry spin. Combining quantum mechanics with special relativity does not merely permit spin, it requires it. Electron spin of 1/2 is as inevitable as electron charge. As inevitable as the existence of the positron. The rotation we have traced from galaxies down through solar systems, down through atoms, is inherited at all those scales. But at the bottom, at the level of the fundamental particles themselves, it is not inherited from anything. It is intrinsic, built into what a particle is. Not spinning is mathematically impossible for a particle described by the Dirac equation. And now the second question, the deeper one. Not what spin is, but what spin does. The same year that Goudsmit and Uhlenbeck proposed electron spin, Wolfgang Pauli formulated something else. This is not a coincidence of timing. The 2 ideas were addressing the same underlying reality from different angles. Pauli's exclusion principle. No 2 identical fermions, no 2 particles with half-integer spin can occupy the same quantum state at the same time. Not the same position with the same energy and the same spin orientation. Forbidden. Completely, universally, without exception. Think about what this means for an atom. The lowest energy level in an atom can hold 2 electrons. 2, not 3, not 10. Why 2? Because there are only 2 possible spin states, up and down. 2 electrons can share that level if and only if their spins are opposite. A third electron cannot fit. Its spin, whether up or down, would duplicate the quantum state of one of the 2 already there. Forbidden. So it goes to the next level, and the next electron after that, and the one after that. Shell by shell, level by level, the electrons fill upward. This generates the periodic table, not as a classification system invented for convenience, as a physical consequence of the Pauli principle. Each element has a distinct electron configuration because no 2 electrons in the same atom can occupy the same quantum state. Hydrogen is not helium, carbon is not oxygen, iron is not gold. The differences are real and permanent because the exclusion principle makes them unavoidable. Remove spin from the picture entirely. Set it to 0. Imagine electrons with no intrinsic angular momentum, no exclusion principle, no forbidden states. Every electron in every atom collapses to the lowest available energy level. All of them. Every element would have the same electronic structure. Every atom would be chemically identical. The periodic table disappears. Chemical bonds cannot form because bonds depend on the different chemical properties that arise from different electron configurations. Molecules cannot exist. Carbon chemistry does not happen. Water is not a molecule. Organic chemistry has nothing to work with. Biochemistry has nothing to work with. Life has nothing to work with. Not a less interesting universe. A fundamentally structureless one. There is a second consequence that is closer to daily experience. When you press your hand against a table, what stops your hand from passing through? The standard answer is that atoms are hard little balls pushing back. But atoms are not hard little balls. An atom is mostly empty space. The nucleus is vanishingly small. The electron cloud surrounding it is the atom's effective size. And that cloud is not a solid surface. What stops your hand is not electromagnetic repulsion, though that exists too. At the most fundamental level, it is the Pauli exclusion principle. When the electron clouds of your hand and the table overlap, electrons from both would be forced into shared quantum states. They cannot occupy the same quantum state. The exclusion principle generates an effective repulsive pressure, a pressure with no classical analog, not a contact force between spheres, a quantum statistical resistance to state sharing. This is called electron degeneracy pressure, the pressure arising from the exclusion of identical fermion states. Electron degeneracy pressure is what makes matter occupy space. It reaches further than tables and hands. When a star like the Sun exhausts its nuclear fuel, gravity begins to win. The core collapses inward. At a certain density, the electrons are so tightly packed that the exclusion principle pushes back against further compression. Electron degeneracy pressure halts the collapse. The result is a white dwarf, a stellar remnant roughly the size of the Earth, supported not by fusion, not by thermal pressure, but by quantum statistics, by the impossibility of forcing electrons into shared states. Push harder, and the electrons merge with protons to form neutrons. Neutrons are also spin 1/2 particles. They are also fermions. They also obey the exclusion principle. Neutron degeneracy pressure, the same principle applied to neutrons, halts the collapse at the next stage. The result is a neutron star. The floor under your feet and the neutron star resisting gravitational collapse are governed by the same underlying rule. The same spin property that cannot be visualized, that cannot be described as rotation, that emerged as a mathematical necessity from Dirac's equation, is the rule that stops matter from passing through itself and prevents stellar remnants from collapsing into nothing. Spin is not a peripheral detail of particle physics. It is the load-bearing structure of physical reality. Remove it, and the universe has no periodic table, no chemistry, no molecules, no solids, no stars held at the edge of collapse. Remove it, and the observable universe is a featureless plasma with nothing to distinguish one patch from another. Keep it, and you get the layered, structured, chemically complex universe that eventually produces the atoms that look back at themselves and ask what spin actually is. That question is still open, but what spin makes possible is not. And the consequences do not end at the scale of electrons and neutron stars. Spin generates something even stranger at the boundary between particles and fields. something that divides the entire content of the universe into two camps that cannot trade places and will never mix. Those two camps are not evenly matched, and the rules that separate them are not arbitrary. The universe divides all of its content into exactly two categories: fermions and bosons. Particles with half-integer spin, like electrons and quarks, fall into the first group. Particles with integer spin, like photons and gluons, fall into the second. That division sounds like a classification system, the way a biologist might sort species into genus and family. But it is not a classification. It is a mathematical consequence. The universe does not organize particles into two groups because it finds the grouping convenient. It organizes them because space-time symmetry leaves no other option. This is the spin statistics theorem. It is one of the deepest results in quantum field theory, the branch of physics that describes particles as excitations of underlying fields. The theorem says that half-integer spin particles must obey Fermi-Dirac statistics, the rules governing how fermions share quantum states, and integer spin particles must obey Bose-Einstein statistics, the rules governing how bosons behave collectively. You cannot mix the two. You cannot create a particle that partially obeys one and partially obeys the other. There is no third category, no gradation between them, no middle ground. Richard Feynman, one of the physicists most gifted at turning abstract mathematics into human-scale understanding, publicly admitted he could not give an elementary intuitive explanation of why spin determines statistics. Not because he hadn't tried, because the proof genuinely does not have a simple, everyday analog. It requires Lorentz invariance, the principle that the laws of physics look identical in every inertial reference frame, combined with causality, the requirement that events cannot influence each other faster than light. Those two constraints together force quantum fields to either commute or anti-commute at space-like separations, meaning at separations where no signal could travel between the 2 points in time for the measurement. Integer spin fields commute. Half-integer fields anti-commute. That last sentence contains the entire mechanism. Anti-commutation is what produces the Pauli exclusion principle. When you work out the mathematics of a half-integer field under anti-commutation, the result forces any two identical fermions into different quantum states, not as an additional rule bolted onto the theory, as a direct output of the anti-commutation relation itself. The exclusion principle is not a separate law, it is a consequence of how half-integer fields must behave given the symmetries of spacetime. Here is where the implications become clear. Spin is not a property that particles happen to carry the way a car happens to have a certain color. Spin is the signature of how a particle transforms under the symmetries of spacetime. It tells you how the particle's quantum state rotates when you rotate your reference frame, and that transformation rule, derived from Lorentz invariance, is what forces the particle into one of the two statistical categories. The connection between spin and statistics is mathematically forced. The structure of matter follows. The Standard Model, the most precisely tested physical theory in history, is organized by spin. The force carriers, the particles that mediate interactions between matter, are all spin 1. The photon carries the electromagnetic force. Gluons carry the strong nuclear force. The W and Z bosons carry the weak force, all spin 1. The Higgs boson, which interacts differently, is spin 0. If the graviton exists as a quantized particle, it would be spin 2. These are not coincidences. Spin determines the mathematical structure of a force. It determines how many polarization states the carrier has, how the interaction depends on direction, how it couples to matter. Spin is the organizing principle. The entire catalogue of particles and forces is written in spin values. And underneath it all, angular momentum is conserved. Every interaction, every decay, every emission, every collision preserves the total angular momentum of the system to extraordinary precision. Not approximately. Not most of the time. Exactly. The universe keeps perfect books. Every spin you can measure today inherited its existence from some earlier configuration. Trace the chain backward, and it reaches the earliest moments of the universe. Physics tells you precisely how the ledger evolves. It cannot tell you how it began. The answer was stranger than expected. Conservation laws are simultaneously the most powerful tools in physics, and the most unsatisfying. They tell you that whatever the opening balance was, the total will stay constant through every subsequent transaction. They do not tell you what opened the account. Every galaxy you can see is spinning. Every star, every planet, all of that angular momentum is real, measurable, and conserved. The natural assumption is that it was inherited from primordial conditions, seeded at the beginning and carried forward. But inflation destroys that assumption. In the first tiny fraction of a second after the universe began, space itself expanded at an extraordinary rate. The inflationary epoch multiplied the volume of the universe by at least 10 to the power of 78. To put that in terms that carry some weight, that is a 1 followed by 78 zeros. Any net global angular momentum that existed before inflation would have been stretched across a volume so incomprehensibly large that its density would be effectively zero. Not reduced to a small value, reduced to something unmeasurable, indistinguishable from nothing. So the angular momentum of every spinning galaxy cannot be a direct inheritance from a single primordial global spin. Inflation erased that inheritance. Wait, then where did all of today's rotation come from? The answer was worked out in 1951 by Fred Hoyle and extended over the following decades by Philip Peebles and others. The theory is called tidal torque theory, and it describes a mechanism that does not require primordial global spin at all. After inflation, the universe was not perfectly uniform. There were slight variations in density, regions fractionally denser or slightly less dense than the average. These perturbations were seeded by quantum fluctuations during the inflationary epoch itself, microscopic variations that the rapid expansion froze into the large-scale structure of space. As gravity slowly amplified these fluctuations over hundreds of millions of years, dense regions began to collapse inward, forming the seeds of what would eventually become galaxies. Here is the mechanism. Two neighboring proto-galactic structures collapsing under gravity are not perfectly symmetric with respect to each other. One is not a perfect sphere, neither is the other. As they collapse, each exerts a gravitational tidal force on the other, a differential pull that is not identical across the entire extent of the neighboring structure. Those tidal forces transfer angular momentum between the two collapsing regions. And this is the crucial point. Angular momentum is not created. It is exchanged. One structure gains spin in one direction, the other gains spin in the opposite direction. The total remains unchanged. But locally, each structure has acquired rotation from its interaction with a neighbor. You end up with a universe full of spinning galaxies whose rotation emerged not from a primordial global spin, but from an elaborate network of gravitational trades during structure formation. Tidal torque theory matches the broad statistics of observed galaxy spins reasonably well. but not in every detail. Predictions for individual galaxy spin magnitudes and orientations remain imprecise. The relationship between galaxy spin and the large-scale cosmic web, the vast network of filaments and voids that structures the universe at its largest scales, is not fully explained. It is an active area of research. The theory captures the mechanism. It does not yet capture everything that mechanism produces. Step back from the details and the picture that emerges is remarkable. The angular momentum of every spinning structure in the universe, every galaxy, every star, every planet, is traceable to amplified quantum fluctuations from the first fraction of a second of cosmic history, exchanged via gravitational tidal forces during structure formation, and conserved at every step along the way. A galaxy is, in a precise sense, the grown-up version of a quantum fluctuation in the earliest moments of time. The universe converted quantum noise into cosmic structure, and rotation came along as part of that structure. But the deepest question remains unanswered. Why did those initial quantum fluctuations contain the angular momentum they did? What determined the rotational content of the universe's opening conditions? That is not a question tidal torque theory can answer. That is not a question any current theory can answer. It sits at the boundary where physics describes the evolution of the universe and falls silent about its origin. The ledger is perfectly kept. The first entry is unexplained, and the first entry turns out to be only one of several things about rotation that physics can describe with extraordinary precision and cannot yet fully explain. Set that question aside for a moment. Set aside where each galaxy's spin came from, the tidal exchanges, the quantum fluctuations, the long chain of amplification and conservation. Set all of that aside and ask the simplest possible question instead. What does it all add up to? Take every galaxy in the observable universe. There are roughly 2 trillion of them. Take each one's angular momentum, its spin direction, its rotation speed, its mass. Record the number. Now take the orbital angular momentum of galaxies moving around each other inside clusters. Take the spin of every star inside every galaxy. Take every planet orbiting every star. Take every neutron star, rotating hundreds of times per second, carrying more angular momentum per unit volume than almost anything else in existence. Take every black hole, carrying the spin of every star that collapsed to form it. Sum everything, every direction, every speed, every mass. 2 trillion galaxies and everything inside them. The result is essentially 0. Not small relative to the total. Not a modest residual. 0, within the limits of what we can measure. The positive angular momenta and the negative angular momenta cancel each other to extraordinary precision. The universe is full of rotation at every scale, and the whole of it sums to nothing. This should stop you. Think about what that means. 2 trillion galaxies, each one spinning, each one containing hundreds of billions of stars, each of those stars orbited by planets, and when you do the full accounting, it all cancels. The universe carries no net rotation. Globally, it does not spin. The evidence is not just in the galaxy counts. We have an independent check. The cosmic microwave background, the afterglow of the early hot universe, fills the entire sky with light that left the universe when it was about 380,000 years old. That light carries a record of what the universe looked like before any galaxies formed. The temperature of that light varies across the sky, but only barely. The variations are about 1 part in 100,000, a fluctuation smaller than the width of a human hair compared to the height of the Empire State Building. And embedded in those variations is everything about the early universe's structure, its density fluctuations, its geometry. What the CMB does not contain is any large-scale rotational pattern, no asymmetry indicating the universe was spinning when that light was released, no preferred axis of rotation imprinted on the sky. The global rotation, if any existed at that early moment, was below any level the CMB shows. Every piece spins. The whole does not. This is deeply strange, and the strangeness reaches further than the arithmetic of the cancellation. A universe with net global rotation would not violate any known physical law. The equations of general relativity even permit exact solutions describing a rotating universe. These solutions exist. The mathematics allows them. A rotating universe is a physically consistent possibility. The fact that ours does not rotate is not something the laws of physics forbid. It is something the initial conditions of our universe happen to produce. No symmetry principle obviously demands it. No conservation law requires it. The universe could have started spinning, and nothing in the physics would have said no. So why doesn't it? Some cosmologists point to inflation, the same rapid expansion that smoothed the geometry of the early universe, stretching any curvature toward flatness, stretching any matter non-uniformity toward homogeneity, may also have stretched any primordial global rotation toward zero. If the universe began with some net angular momentum, inflation would have diluted its density across the expanded volume until it became undetectable. On that account, the zero is not a feature of the universe's origin, but a consequence of the expansion erasing what was there. But tidal torque theory offers a different perspective. Recall how galactic rotation arises. Neighboring proto-galactic structures exchange angular momentum through gravitational tides. One structure gains spin in one direction. Its neighbor gains spin in the opposite direction. The total is conserved, but locally distributed. This mechanism inherently produces local angular momenta without producing net global angular momentum. The cancellation between neighbors is built into the exchange itself. On that account, the zero is a statistical consequence of how angular momentum is distributed during structure formation, not a statement about the origin. Neither explanation is conclusive. Inflation provides a plausible mechanism for erasing primordial rotation, but does not explain what set the initial conditions before inflation. Tidal torque theory explains why the local exchanges cancel globally, but does not explain why the mechanism was structured that way from the start. Both accounts describe physics that would produce the observed result. Neither one makes the result inevitable. The precision is what demands attention. 2 trillion galaxies, with spins oriented in every direction, at every speed, with every mass, and they cancel to within current measurement capability. The universe is like a collection of spinning tops arranged so their angular momentum vectors point in directions that sum to a point. Every top is spinning. The arrangement is still, not because the tops slow down, because the directions are set so the motions undo each other. Imagine a gyroscope spinning internally, its rotor turning at high speed, and yet the gyroscope as a whole is not precessing, not turning, not moving through space. The internal motion is real. The aggregate motion is zero. Something in the setup produced that stillness. 2 trillion galaxies play out that same balance across the entire observable universe. But here is the question the accounting cannot close. Is the cancellation exactly zero, or only approximately zero? Those are different statements about reality. A result of exactly zero would suggest an undiscovered principle, a symmetry or conservation law we have not yet identified that forbids global rotation as rigorously as charge is conserved or energy is conserved. A result of approximately zero, very small but not precisely nothing, would suggest the cancellation is statistical, a consequence of distribution and exchange, with a tiny residual hiding below detection thresholds. We cannot currently distinguish between these two possibilities. Our instruments measure a global rotation consistent with zero, but consistent with zero is not the same as proven zero. There could be a residual, it could be small enough that no telescope or CMB map yet built has the sensitivity to detect it. The question is genuinely open, and that question, it turns out, is not purely an astrophysical one. The answer has implications that reach into the foundations of cosmology and beyond, into questions about the nature of space-time and what the universe's rotation, or its absence, says about the structure of physical law at the deepest level. That is where the next layer of this story begins. So the question remains open. There could be a residual. And now the question shifts from whether there is a residual to what would actually be at stake if there were. The most fundamental claim in modern cosmology is something called the cosmological principle. It states that on the larger scales, the universe looks the same everywhere and in every direction. Homogeneous, meaning no privileged location. Isotropic, meaning no privileged direction. These are approximations at small scales where galaxies cluster and filaments thread through voids. But zoom out far enough and the universe smooths into something very close to uniform. The cosmic microwave background is the best evidence for this. The light released when the universe was about 380,000 years old arrives from every direction at nearly the same temperature. The variations are less than 1 part in 100,000. That is not a small difference. It is almost no difference at all. The universe, in its earliest observable state, was extraordinarily close to the same in every direction. A rotating universe would violate this. Rotation has an axis. An axis creates a preferred direction. A preferred direction breaks isotropy. The cosmological principle would fail, and everything built on it, all of standard cosmology, every model of structure formation and dark energy and the large-scale geometry of space would need to be reconsidered from the foundations. The Planck satellite, which mapped the cosmic microwave background with greater precision than any instrument before it, has set the tightest limits available on possible global rotation. The upper bound on the universe's rotation rate is approximately 10 to the -9 radians per Hubble time. 1 Hubble time is roughly the age of the universe. So if the universe is rotating at all, it has completed at most 1 billionth of a single radian over its entire existence. Think about what that means in practice. A full rotation is about 6¼ radians. 1 billionth of a radian is not a fraction of a full turn. It is a fraction so small it has no useful everyday comparison. If you were watching the universe rotate from outside, you would detect nothing. No drift, no shift, no movement over billions of years of observation. For all practical purposes, the number is 0, but it is not proven to be exactly 0. That gap between practically 0 and provably 0 turns out to matter more than it might seem. There have been claims, contested but not yet settled, that a residual might already be visible. Lior Shamir, a computer scientist and astronomer, has analyzed large catalogs of galaxy images and argued that galaxies rotating in one direction outnumber those rotating the opposite way by roughly 3%. Not a large effect, not something obvious to the eye, But Shamir argues the asymmetry is statistically significant and varies in a pattern across the sky, which would suggest a preferred handedness in the cosmic structure, a faint global chirality that could be the signature of very weak global rotation. Most cosmologists are skeptical. The effect is small. The methods are disputed. Automated image classification systems, which sort galaxies by the direction of their spiral arms, can carry asymmetric errors. A bias in the algorithm could produce exactly the kind of asymmetry Shamir is measuring, with no rotation in the universe at all. The debate has not been resolved. Future surveys with better instruments and independent analysis pipelines may settle it. For now, it sits in the uncomfortable category of claims that cannot be confirmed and cannot quite be dismissed, but the picture did not hold. The question of whether the universe has a small residual rotation is not merely a question about the shape of galaxy catalogs or the precision of CMB measurements. It connects, through a piece of mathematics worked out 75 years ago, to whether time itself could be broken. April 28, 1949. Princeton, a conference organized to celebrate Albert Einstein's 70th birthday. Scientists and mathematicians gathered to honor him, and several presented papers on the implications of his work. One of the presenters was Kurt Gödel. Gödel was already one of the most famous figures in 20th century mathematics. In 1931, he had published 2 incompleteness theorems that ended Hilbert's program, the decades-long effort to build mathematics on a complete and consistent formal foundation. Gödel proved that any sufficiently powerful formal system will always contain true statements that cannot be proved within that system. The dream of a fully grounded mathematics, rigorous all the way down, was not merely unfulfilled, it was unfulfillable. At Einstein's birthday conference, Gödel arrived with a gift, not a tribute, a problem. He had found an exact solution to Einstein's field equations of general relativity. The field equations describe how matter and energy curve space-time, and they have many possible solutions corresponding to different possible universes. Gödel had worked out a solution describing a universe in which matter is uniformly distributed throughout space, consistent with the cosmological principle, but rotating. The matter itself rotates. The universe has a global angular momentum. The solution was mathematically valid, not an approximation, not a special case requiring unusual assumptions, an exact solution to Einstein's own equations. And in that solution, something catastrophic followed. In Gödel's rotating universe, a sufficiently motivated traveler following a specific path through space-time, accelerating and curving over a large enough journey, could arrive back at the same point in space, at the same moment in time they had departed. Not the same location after a long journey, the same moment. A closed time-like curve, a path through space-time that loops back to its own origin in time. Travel into one's own past, permitted by general relativity. The mechanism is geometric. In ordinary flat or gently curved space-time, light cones define the causal structure of reality. The future light cone from any event contains all the events that event can influence. The past light cone contains all the events that could have influenced it. The cones point cleanly forward in time. Cause precedes effect. The arrow of time is unambiguous. Rotation changes this. The rotation of matter in Gödel's universe creates an effect on space-time structure similar to the way a rotating mass drags nearby space-time around with it. A gravito-magnetic-like warping of the geometry. This tilts the light cones, not a little, enough that the future light cone, the region of space-time you can reach, eventually curves around far enough that it overlaps with your own past. The region of space-time accessible to you contains events that, by the ordinary logic of cause and effect, already happened to you. You can reach them. Closed time-like curves become possible. Causal paradoxes follow. Prevent your own birth. Deliver information to your earlier self that you only learned because your earlier self received it. The logical structures that underpin the ordinary experience of time come apart. Stephen Hawking argued against this. His chronological protection conjecture holds that the laws of physics conspire to prevent closed time-like curves from forming in any physically realizable scenario. The argument is not that Gödel was wrong mathematically. The mathematics is correct. The argument is that a universe permitting causality violation would be so physically pathological that quantum effects, or thermodynamic constraints, or some as yet unidentified mechanism would always intervene to block the conditions that would allow such curves to form. Roger Penrose contributed related work on the pathologies of rotating spacetimes and the conditions under which physical collapse or divergence would precede any causal violation. The chronological protection conjecture is still a conjecture. It has not been proved. Our universe does not appear to be Gödel's universe. We observe no global rotation above the Planck satellite limits. We observe no closed time-like curves. The CMB is isotropic to within 1 part in 100,000. Every measurement is consistent with a non-rotating expanding universe, not a rotating one, but the linkage is real. Gödel did not describe a science fiction scenario. He found it inside Einstein's equations. The connection between global rotation and causal structure is not a philosophical speculation. It is a mathematical derivation from the same framework that predicts black holes and gravitational waves, both of which we have confirmed exist. This reframes the cosmic zero in a way that earlier sections of this story could not. The sum of the universe's angular momentum comes to essentially zero. The CMB shows no rotational signature. The Planck limits confine any residual rotation to an almost inconceivably small upper bound. All of this might simply be the initial conditions the universe happened to start with, a statistical outcome with no deeper significance, a fortunate coincidence with nothing behind it, or it might be necessary. If a universe with significant global rotation is a universe where the causal structure of space-time is compromised, where closed time-like curves become possible, where the arrow of time might not point cleanly forward everywhere, then perhaps no such universe could develop the sustained ordered complexity that time itself seems to require. No chemistry, no evolution, no sequences of causes building toward effects. Perhaps only a non-rotating universe, one where the light cones remain well ordered, where causality holds everywhere, can be a universe in which anything that depends on time actually happens. The zero may not be an accident. It may be a condition. Either way, it is doing more work than its size suggests. And the question of whether the residual is precisely nothing, or merely too small to yet detect, may be the most consequential measurement in cosmology that no one has yet been able to make. That question, whether the zero is exactly nothing or merely too small to see, sits at the edge of what current physics can answer. But there is a different kind of why underneath it. Not why is the number so small, but why must the number stay constant at all? Why does angular momentum persist? Why does the universe bother conserving it? Those questions lead somewhere deeper. The year was 1915. A German mathematician named Emmy Noether proved what may be the single most powerful result in all of theoretical physics. It connects two ideas that seem unrelated. The the symmetries of physical law, and the things that physical law preserves. Here is what no other showed. Every continuous symmetry of the laws of physics corresponds to a conserved quantity, not approximately, not in certain conditions, exactly, always without exception. The logic runs like this. If the laws of physics are the same today as they were yesterday, if no experiment done now would give a different result from the same experiment done a week ago, then that time translation symmetry guarantees conservation of energy. If the laws are the same here as they are in another room, in another galaxy, then that space translation symmetry guarantees conservation of momentum. And if the laws of physics have no preferred direction, if no experiment has ever found any axis in space that physics treats differently from any other, then that rotational symmetry guarantees conservation of angular momentum. The law is upheld by no enforcement mechanism. No monitor checks the books, no force steps in when spin tries to disappear. The conservation holds because the symmetry holds. That is all it takes. That is all it needs. And the rotational symmetry of physical law appears to be exact. Physicists call the formal structure SO3, the group of all rotations in three-dimensional space. As far as any experiment has probed, it holds without deviation. No preferred direction has ever been measured. No axis has ever been found. Because the symmetry is continuous and exact, Noether's theorem guarantees that angular momentum is conserved continuously and exactly in every process at every scale. This is why the conservation chain holds from quantum spin in a hydrogen atom to the orbital momentum of the Milky Way through the Virgo cluster. The same symmetry reaches across every scale. The same law holds everywhere. There is no enforcement, only symmetry, but the picture was incomplete. Noether's theorem is a statement about dynamics. It describes how a system evolves from one moment to the next, and it says, whatever angular momentum you have, you will keep. The theorem says nothing about how much you started with, nothing about where the opening balance came from. Conservation is a constraint on evolution. It is silent on initial conditions. Think about what that means. The laws of physics could be perfectly rotationally symmetric. Noether's theorem fully satisfied, angular momentum perfectly conserved, and the universe could have begun with zero spin, or with 1 trillion times more than it has, or with a specific non-zero direction baked into the geometry from the first instant. All of those starting points are consistent with the symmetry. The symmetry says none of them will change during the history of the universe. It does not say which one was chosen. This is not a flaw in Noether's theorem. It is the nature of physical law. Laws describe regularities in evolution. Initial conditions are by definition prior to evolution. The Standard Model does not predict the mass of the electron. It accepts it as an input. General relativity does not predict the total mass energy content of the universe. It accepts that too. Initial conditions are the boundary conditions of the theory, not its solutions. They are the starting point the equations need before they can run. Some physicists have tried to reach past this boundary. The Hartle-Hawking no-boundary proposal, developed in quantum cosmology, suggests that the universe had no temporal beginning in the ordinary sense. In that picture, the universe emerged from a quantum geometry without a singular starting moment, and its initial conditions might be self-selected by quantum self-consistency rather than simply given. If correct, the angular momentum content of the universe might follow from the geometry of that quantum birth. Whether the proposal gives zero net angular momentum, whether it is even the right framework, Both of those remain open questions. What is not open is this: the answer to why everything spins cannot come from conservation laws alone. Noether's theorem tells us spin will be preserved. It has nothing to say about why there was any spin to preserve. The theorem closes one door, it opens another one that goes deeper still. The pivot the documentary has been building toward without naming it is this: throughout every scale we have examined, the framing has been consistent. Space is the container. Rotation is the content. Objects exist in space. Objects spin. The container precedes what it holds. But what if the relationship is reversed? This is not a metaphor. It is an active, rigorous program in quantum gravity research, developed independently along two separate lines, arriving at the same unsettling conclusion. The first line begins in the late 1980s, with physicists Carlo Rovelli and Lee Smolin developing what became loop quantum gravity. The goal was to quantize general relativity, to apply the same discrete, packet-based description that quantum mechanics uses for matter and energy to geometry itself, to space and time. What they found, working through the mathematics, was that smooth space does not survive the transition to quantum scales. At the smallest scale, roughly 10 to the negative 35 meters, space is not a continuous background. That scale is called the Planck length. If you took a single atom and magnified it until it was as large as the observable universe, a Planck length would still be smaller than an atom. Below that scale, smooth geometry breaks down entirely. What replaces it is a spin network, a mathematical graph of nodes connected by edges. Each edge carries a label, a value of quantum spin, not the spin of any particular particle, just spin as a pure mathematical quantity assigned to the connections between nodes. And here is the part that changes everything. Those spin values are not labels describing the geometry. They are the geometry. The area of a surface in the network is determined by the spins of edges crossing it. The volume of a region is determined by the spins of the nodes within it. Area and volume are quantized. They come in discrete minimum units, the way electric charge comes in units, and the way photon energy comes in packets. Below the Planck scale, there is no smaller spatial structure. Space is granular at its foundation. The smooth space we experience, from the scale of a molecule to the scale of a galaxy cluster, is emergent. It is a macroscopic average over an enormous number of discrete spin-bearing edges and nodes. The way the smooth surface of water emerges from the collective behavior of individual molecules that are themselves not smooth, not continuous, not anything like the surface they collectively produce. Not rotation inside space, rotation as the raw material from which space is built. The second line begins in the 1960s with Roger Penrose pursuing a different problem. Penrose was troubled by the fact that quantum mechanics and space-time geometry use radically different mathematical languages. He wanted to find a more fundamental structure that unified them. The result was twistor theory. In twistor theory, the fundamental objects are not points in space-time. They are twistors, geometric structures that encode momentum, energy, and angular momentum together. The primary objects are null rays, light rays with associated angular momentum. A point in space-time does not correspond to a single twistor. It corresponds to an entire sphere of twistors. Space-time events are not primary objects in the theory. They are secondary, derived structures emerging from the intersections of spinning-directed structures. Reality, in the twistor picture, is built from spinning geometries. The four-dimensional space-time stage we perceive is a reconstruction at a coarser level. The spinning is primary. The space is the projection. In 2003, Edward Witten showed that particle physics amplitudes, the mathematical quantities describing how particles interact and scatter, could be reformulated elegantly in twistor space. Calculations that required enormous Feynman diagrams, pages of complex bookkeeping, became drastically simpler when approached through twistor methods. The simplification was not merely aesthetic. It suggested that twistor space was revealing something genuinely more fundamental about the structure of the interactions. Loop quantum gravity and twistor theory arrived independently. Different motivations, different mathematical machinery, different problems they were designed to solve, but they converge on the same provocative idea. Rotation and angular momentum are not features imposed on a pre-existing spatial stage. They are prior to that stage. They are constitutive of it. If this picture is correct, the question of why everything spins is not a question about the contents of reality. It is a question about what reality is made of. And the candidate answer is spin. Asking why matter spins would be like asking why matter has spatial extent. The question assumes the wrong relationship. Matter does not have spatial extent inside a pre-existing space. Matter and the spatial structure it inhabits are aspects of the same underlying geometry. In the same way, if spin networks or twistors are the right picture, rotation is not a property that things have inside space. It is what space is. Honesty requires saying clearly, this is speculative. Loop, quantum gravity, and twistor theory are both incomplete. Neither has made confirmed experimental predictions at scales where their specific features would become directly observable. The Planck scale sits 16 orders of magnitude below anything any particle accelerator can probe. That is not a gap that a better machine will close in the next decade or the next century. Direct experimental tests of Planck scale structure may not be possible in any practically foreseeable future, but both programs represent serious, rigorous frontier work. They represent what physicists actually explore when they ask what space, time, and matter are at their most irreducible level. And the direction the answer keeps pointing is the same. Spin not as a property within reality. Spin as the structure of reality itself, all the way down to the bottom. The conservation that Noether's theorem guarantees. The spin that moves through every scale we have traced across this story may not be a property that exists inside space-time. It may be the architecture from which space-time is drawn. What the universe is conserving at every scale, in every process, through every interaction, may be the very thing it is made of. And that reframing opens a question even deeper than why angular momentum is conserved. It opens the question of what conservation means when the thing being conserved is not a property of the universe, but the fabric of it. That question reaches further than any instrument we have built. And before arriving at it fully, there is something humbler to face first. Even setting aside what space is made of, even staying well inside the territory physics has mapped with confidence, there is an accounting problem, not with the law itself. The law holds everywhere, tested to parts per billion precision, no confirmed exception across the entire history of scientific observation. The problem is with the plumbing. We know the ledger balances. We do not always know how the transactions happen. Here is the clearest example in all of astrophysics. A molecular cloud begins to collapse under its own gravity. It has angular momentum, measurable and real, carried by the slow, turbulent rotation of its gas. Conservation demands that as the cloud shrinks, that angular momentum is preserved. The calculation is straightforward. If no mechanism transferred that angular momentum away, The collapsing material would spin faster and faster until centrifugal force halted the infall entirely. You would get a large, rapidly rotating disk. You would not get a star. The cloud's own angular momentum would prevent it from ever becoming the thing gravity was trying to build. But stars exist, so something must carry the angular momentum away. Physicists have identified 4 mechanisms: magnetic braking, where field lines threaded through the cloud act as a lever transferring angular momentum from the collapsing inner material outward into the slower surrounding medium. Gravitational torques from binary companions. Since most stars form in pairs or multiples, and the gravitational interaction between forming neighbors moves angular momentum on relevant timescales. Outflows and jets, collimated beams of material launched perpendicular to the disk at hundreds of kilometers per second, extending light years beyond the forming system, acting as an exhaust valve for excess angular momentum. And disk accretion driven by the magnetorotational instability, a process where magnetic fields make the disk turbulent in a precise way that moves angular momentum outward while mass spirals inward toward the forming star. All 4 operate simultaneously in any real star-forming system. The ALMA telescope, the Atacama Large Millimeter Array in Chile, has revealed disk structures around very young stars that are still being interpreted. And here is where the humility becomes sharp. None of these 4 mechanisms, not individually, not in combination, can yet predict from first principles the spin rate of a newly formed star. Given the initial conditions of a specific molecular cloud, no calculation currently produces a reliable answer for how fast the resulting star will rotate. The conservation law is exact. The redistribution machinery is incomplete. The same gap appears at every other scale. Galaxy formation simulations reproduce the broad statistics of how galaxies rotate and how their angular momenta correlate with mass and position in the cosmic web of filaments and voids. But those simulations depend on feedback prescriptions, approximate descriptions of how supernovae, stellar winds, and jets from supermassive black holes inject energy and momentum into surrounding gas. These prescriptions are not derived from first principles. They are calibrated against observations because the physical scales involved are too extreme to calculate directly. A single supernova must influence surrounding gas at scales thousands of light years larger than the explosion itself. Resolving both simultaneously, even on the fastest computers available, is not possible. Whether any individual galaxy's spin can be reliably predicted from the initial conditions of its host, dark matter, halo remains open. And then there is the Earth. About 4.5 billion years ago, a Mars-sized body called Theia struck the early Earth in a glancing blow. The giant impact model is the leading explanation for how the Moon formed. Molten material ejected from the collision coalesced into the Moon, which is why the Moon's mantle composition resembles Earth's mantle, and why the Moon has so little iron. The model must also account for the total angular momentum of the Earth-Moon system as it exists today. Some giant impact simulations reproduce this naturally. Others require careful tuning of impact angle, speed, and mass. The parameter space is large. The constraints are real. The exact conditions of that collision 4.5 billion years ago remain unsettled. But the story did not end there. That collision is still unfolding. Tidal forces between Earth and Moon are continuously transferring angular momentum from Earth's rotation to the Moon's orbit. The Moon is currently moving away from Earth at roughly 3.8 centimeters per year, measured by laser pulses bounced off retroreflectors placed on the lunar surface by the Apollo missions. Earth's rotation is correspondingly slowing by about 1.4 milliseconds per century. Not much by any everyday standard, but accumulated over billions of years, the effect becomes dramatic. Billions of years ago, the moon was perhaps 1/3 its current distance from Earth. Earth's rotation was much faster. A day may have been 6 hours long rather than 24. Tidal dissipation was far more intense. The oceans driven by a moon that filled a larger arc of sky. We know this from geologists studying tidal rhythms preserved in ancient sedimentary rocks, astronomers measuring the current recession rate, and dynamicists modeling the coupled evolution of the system across deep time. 3 separate lines of evidence, all pointing to the same slow outward spiral, the same gradual lengthening of the day. Conservation solved, plumbing incomplete, pattern confirmed at every scale. And yet, consider what the conservation law actually accomplishes, despite everything it cannot predict. The same mathematical relationship that keeps an ice skater spinning faster when she pulls her arms in, a relationship derivable by any undergraduate student in an afternoon, also keeps the Milky Way rotating at 230 kilometers per second, billions of years after the gas cloud that formed it was consumed. One law, 20 orders of magnitude in physical scale, every spinning object in the observable universe. The ledger always balances. We just do not always know exactly who carried each entry. That gap is not a failure of physics. It is normal science working at the boundary of what current instruments and computers can resolve. Better telescopes, faster simulations, sharper measurements will close parts of it. But the gap between conservation and mechanism has always been present, and it is worth naming honestly before arriving at a much deeper one, because the conservation question has 2 layers, and only one of them has been answered. The first layer: why do spinning things keep spinning? Why does angular momentum persist? Why do bound systems naturally form rotating structures? Why disks and not spheres? Why does the skater spin faster when she pulls her arms in? Why will the Milky Way still be turning long after the sun is gone? Those questions have answers. Noether's theorem, rotational symmetry of physical law, conservation as the mathematical consequence of that symmetry, the physics of gravitational collapse, accretion disk dynamics, tidal torques theory, not complete in every quantitative detail, but understood in outline. The first layer is answered. The second layer is not. Why did the universe begin with the angular momentum it began with? Why did the initial conditions contain spin at all rather than being rotationally empty? Every particle has spin. Every gravitationally bound structure rotates. Every disk in the cosmos, Saturn's rings, the solar system, neutron star accretion disks, the blazing disks around supermassive black holes and quasars across the visible universe, is angular momentum that could not fall into the central object, and instead organized itself into the flattest, most rotationally efficient geometry it could find. Every disk is a fossil. Every ring is a memory. Every spiral arm is angular momentum, writing its own history in starlight. And the total of all of it, 2 trillion galaxies each spinning, orbiting, precessing, summed across the observable universe, cancels to 0 within measurement error, not near 0, not small relative to the individual parts, 0. The vector sum of all angular momentum in the observable universe, as best measured, comes out to nothing. No confirmed exception to conservation has ever been observed. Conservation holds to parts per billion precision in particle physics laboratories, and yet the total sum of what is being so perfectly conserved is apparently nothing. Stop. That is not a technical detail. That is either the most elegant fact in all of cosmology or its most glaring open wound. We do not know why the sum is zero. We do not know whether it is exactly zero or only approximately zero. And that distinction is not a decimal place refinement. A universe with significant net angular momentum is qualitatively different from one without it. Gödel's exact solution to Einstein's equations showed that a rotating universe permits closed time-like curves, paths through space-time that loop back on themselves, making the past geometrically reachable from the future. Whether near-zero global angular momentum is a necessary condition for time to function as a directed dimension, for thermodynamics to hold, for memory and causality and biological complexity to be possible at all, is a question that currently sits at the intersection of physics, cosmology, and philosophy, and has no answer. No theoretical principle requires the global sum to be zero. No working model of quantum cosmology derives the cancellation from something more fundamental. The zero is observed, not explained. The books balance perfectly. Nobody knows who designed the accounting system, or why the opening balance was what it was, and that is the boundary. Physics as currently formulated is an extraordinarily precise description of how the universe's rotational content evolves from whatever initial state it began in. Every calculation, every conserved quantity, every prediction of the standard model or general relativity takes for granted that there was something to start with. The laws describe evolution with extraordinary fidelity. The question of what determined the initial state is outside the frame, not partially answered, not waiting on a faster computer or a more sensitive instrument. Outside the frame of what the laws, as currently written, are structured to address. The laws keep the books with absolute fidelity across the entire history of the cosmos. They have never shown the first deposit. They may not be the right kind of tool for finding it. And so the inventory closes here. Every particle has spin. Every structure rotates. The universe taken as a whole does not spin. Every piece spins. The whole does not. Not as a paradox requiring resolution. As a fact requiring honesty. The universe has been spinning since before time had a name. Every galaxy a wheel turning since before Earth existed. Every star a gyroscope preserving angular momentum from a pre-solar gas cloud. Every atom in the body broadcasting its quantum signature at 1.42 gigahertz into a universe in some sense made of the same thing it is announcing. And somewhere in that structure, in the initial conditions seeding every rotation we have traced from quantum scale to cosmic, in the impossibly precise zero that may be protecting the causal structure of time itself, lies a question the universe has carried since its first moment and not answered. Not because the instruments are too crude, though better ones will be built. Not because the mathematics is too difficult, though it is genuinely hard at this frontier. But because the question reaches past the edge of what the laws of physics, as currently written, are structured to address. The laws describe what happens to spin. They do not say where it came from. They have kept perfect books across the entire history of the cosmos, but they have never shown the first entry. We know how the universe spins. We know it cannot stop. We know that summing all of it returns, impossibly, to nothing. And every time the Earth carries you silently eastward at over 1,000 miles per hour through a night that feels completely still, that stillness is not emptiness. It is the universe perfectly balanced, spinning on a question it has been asking since before there was anyone around to wonder.